Welcome to AI Paper Podcasts. Today we're really digging into a fascinating new paper that tackles a really core challenge for large language models. It's called From Bytes to Ideas, Language Modeling with Autoregressive UNets, and it's coming from a top team, Ferret, Meta, and others involved too. So the basic problem they're looking at is how current language models actually see text. Most of them use this fixed pre-processing step, tokenization, like byte pairing coding, BPE. Think about it like trying to read, but every single word is a solid, unchangeable block. You can't see inside it. This kind of rigidity, well, it limits how well models can grasp fine details or understand new words or even adapt to different languages. It's like they have blinders on.
Exactly. They don't see the internal structure, the morphology.
Right. And the solution they propose is this novel architecture, AUNet, the Autoregressive UNet. And this isn't just a small tweak, it feels like a pretty fundamental shift.
Really is. AUNet learns to embed its own sort of tokens directly from the raw bytes. No fixed dictionary lookup. Instead, it dynamically creates this multi-scale representation of the text.
Like giving the model a zoom lens for language. You can zoom out for context, zoom in for the tiny details.
That's a great way to put it. And the promise here is huge.
Yeah.
Potentially infinite vocabulary, much more flexibility for character level stuff, and better generalization, especially for languages that don't have massive data sets.
Yeah, it's like a big step towards models that are more adaptable, more linguistically aware. So let's unpack this. How does this AUNet actually work? And what does it really mean for AI going forward? We touched on the problem with traditional tokenization. Let's get into the weeds a bit more on why that fixed approach, like BPE, is, well, limiting.
Yeah, so BPE, it's interesting how it works. It essentially builds this dictionary before the model training even starts. It scans a huge text corpus, finds common sequences of bytes or characters.
Like bear becoming the...
Exactly, or maybe eng or ed. It merges the most frequent pairs into new, longer tokens and repeats this until it hits a vocabulary size you decided on beforehand, like, say, 50,000 tokens.
So you predefine the pieces of language the model gets to see.
Right.
And once that's done, it's locked in.
Locked in, that's the key. It creates this fixed granularity. You might have a character level view, PH, or word level, but it's fixed. And there's a trade-off, right? Finer tokens mean longer sequences, way longer. Harder for the model to see long-range connection.
Right, the context window effectively shrinks.
Yeah. And coarser tokens, well, they become rarer, harder to learn, harder to generalize from. And as the person training the model, you basically only have two dials. What text you use to build the vocabulary and how big you make that vocabulary. That's it.
And this leads directly to what the paper calls the opaque identifiers problem. Can you explain that a bit?
Sure. It means each token, whether it's run or running, just gets mapped to its own separate vector, its own ID. The model doesn't inherently see that running is related to run.
It just sees two different unrelated blocks.
Pretty much. They're just opaque labels. It doesn't see the shared run stem or that one is a verb form of the other. It has to learn that relationship from scratch, implicitly from seeing them in context millions of times. And this freezing of the granularity right at the input layer affects everything that follows. All the deeper layers are stuck with this fixed view.
Which really hinders things that need like fine-grained understanding, spelling, morphology.
Symbol level reasoning, yeah. Understanding typos or code or even just adapting to slightly different dialects, it's a real bottleneck.
Okay, so that sets the stage perfectly for AUNet. How does this architecture break free from that rigidity?
The absolute core idea is that AUNet learns to create its embeddings directly from the raw bytes. No static lookup table. It uses attention mechanisms.
Those tools that let the model weigh the importance of different inputs.
Exactly. It uses attention to dynamically figure out the representation as it goes. And the architecture itself is pretty clever. It's inspired by UNets.
UNets, from image processing, right? For segmentation and stuff.
That's the one. They're good at capturing context at different scales. So AUNet borrows that structure. It has a contractive path, an expanding path, just like in image units.
Okay, so contracting path, like zooming out on the text, getting the bigger picture.
Precisely. It works in stages. Stage 1 looks at the raw bytes. Stage 2 might pool information together, say, at word boundaries. Stage 3 could pool after every couple of words. Stage 4 after every 4 words, maybe. You end up with this hierarchy of embeddings. The model isn't just seeing characters or words in isolation. It's building up understanding from tiny pieces to larger chunks. letters, words, phrases, multiple scales at once.
A multi-scale representation built dynamically.
Okay.
And the expanding path reverses that.
Yeah, it reconstructs the sequence. It takes those coarser, zoomed-out vectors from the deeper stages and refines them. It uses specific layers to add detail back in. And critically, it uses skip connections.
Yeah, those are important in UNets too, right? To preserve details.
Vital. They let the model bring fine-grained information, like the exact spelling of a word from the earlier stages, and blend it back in with the broader context captured in the deeper stages, so you don't lose the details when you zoom out.
So it can understand the overall meaning and the precise characters. That's the dynamic granularity.
Exactly. And it leads to this multi-scale prediction idea. The deeper stages, working on the compressed view, are kind of looking further ahead, anticipating broader semantics. They then guide the shallower stages, which handle the finer points, like spelling or local word choice.
And it's all one single architecture, not separate models bolted together.
Right. It's monolithic in that sense. It applies attention across the sequence at each stage, maybe within a sliding window for efficiency, but it ensures things aren't processed totally in isolation. Now, how it splits things up where the word boundaries are, for example, that's currently user-specified, often using spaces for languages like English.
Okay, so that's a detail. Extending it to languages without spaces is future work they mentioned.
Yeah, that's flagged as an important next step. Right now, it relies on something like regular expressions based on spaces.
Got it. So given this whole architecture, what do the authors highlight as the main contributions, the key breakthroughs?
They list out a few key things, C1 through C5 in the paper. First is this adaptive multi-level hierarchy, being able to train up to 4 stages, end-to-end, with user-defined splits. That's a big step beyond earlier hierarchical models that often had fixed pooling or fewer stages.
Right, much more flexible. And that leads to C2, the infinite vocabulary size. That sounds like a game changer.
It really could be. Because it works on bytes, there's no predefined vocabulary limit, no massive embedding table taking up memory. It can, in theory, handle any sequence of bytes, any word, any symbol.
Think about rare words, technical terms, news slang.
Or even code snippets, mathematical symbols, different languages mixed together. It just sees bytes. That's huge.
And crucially, does it actually work?
Yeah.
Contribution C3, strong performance and scaling.
Yes, this is critical. They show that even the shallower AUNets, like 1 or 2 stages, perform pretty much on par with strong BPE baselines on standard benchmarks. And the deeper ones, 3 and 4 stages, show promising scaling. They get better with more data and compute.
So it's not just a cool idea, it's actually competitive.
Exactly. And C4 is practical efficiency. They found it maintains comparable GPU throughput in terms of wall clock time. So it's not drastically slower to train, which is really important for practical adoption. They've also released the code in Metalingua.
Good to know. And finally, C5, stable scaling laws.
Right. Training at the byte level is different. You have much longer sequences. They found you need different formulas to figure out the optimal batch size and learning rate as you scale up compute. They provide those formulas, which is a vital piece for anyone wanting to train these models at scale.
Okay, so the architecture is novel, the potential benefits are clear. Let's look at the proof, the experiments. What did they test it on?
They used a big data set called DCLM. About 4 trillion tokens, mostly English, focused on general language understanding tasks. And for comparison, they set up strong baselines. Standard transformers using the Llama 3 BPE tokenizer, which is a very good tokenizer, plus other byte-level models like byte-level transformers and Mamba.
And making the comparison fair is tricky when one model sees bytes and another sees tokens, right? How do they handle compute budgets?
Yeah, that's crucial. They normalized it. They calculated that on their data set, the BPE tokenizer gives about a 4.56x compression rate. So training AUNet on, say, 273 billion bytes is roughly equivalent, compute-wise, to training the BPE model on 60 billion tokens.
Okay, so they matched the effective amount of data processed.
Yes, and they also did careful work extrapolating the best hyperparameters learning rate, batch size for the bigger models based on tests they ran on smaller versions, necessary when you're dealing with these huge training runs.
Makes sense. So the core results. When they trained models with these equal data budgets, how did AUNet stack up?
The results are pretty impressive. Looking at Table 2 in the paper, AUNet models, especially the 3 and 4 stage versions, consistently matched or actually outperformed the strong BPE baseline on benchmarks like HelloSwag.
That's common sense reasoning.
Right. And ARC, which is general reasoning, and MMLU, the massive multitask language understanding test.
Wow, okay. Outperforming a strong BPE baseline is significant.
It is. There was one interesting outlier initially, TQA, trivia question answering. It's very knowledge intensive. There, the byte-level model started out a bit behind BPE.
Why might that be?
It's possible that BPE tokens, being larger chunks, give a sort of head start on retrieving factual knowledge. But interestingly, that gap closed as the models got bigger, like comparing the 8 billion parameter versions. It suggests it's not a fundamental flaw, but maybe something byte-level models need more scale to fully capture.
Okay, and did they see diminishing returns with more stages? Like, is AUNet 4 always better than 3?
At a fixed data budget, they noted that going beyond 3 or 4 stages didn't always give huge gains. It hints that maybe those really deep hierarchies just need even more data to shine. But overall, AUNet was very competitive, even compared to other byte-level models in the literature that were sometimes trained on more data.
And how does this look when you consider scaling laws? As you pour in more compute, how does AUNet track against BPE?
Looking at their scaling plots, figure 3, the AUNet models, particularly 2 and 3 stages, generally track the performance curve of that strong BPE transformer baseline really well on tasks like HelloSwag, ARC Easy, and natural questions.
So they scale similarly well with compute?
Largely, yes. On TQA, remember where it lagged initially? The 3-stage AUNet actually catches up to BPE at higher compute levels, around 122 FLOPs.
Interesting. So scale helps there.
Definitely.
Yeah.
For MMLU and the math benchmark GSM-8K, the improvement curve for AUNet seemed to kick in a bit later compared to BPE, but they acknowledge the DCLM dataset isn't super rich in math data, so all the models struggled a bit on GSM-8K.
Right, dataset limitations.
But here's a really striking point. Both their AUNet models and their own BPE baseline achieved results surprisingly close to much, much larger models like Llama 3.18b, which was trained on something like 100 times more compute.
Wow. So their baselines are strong, and AUNet matches that strong baseline. That speaks volumes about efficiency.
It really does. It shows AUNet isn't just matching a baseline, it's matching a very competitive one and doing it efficiently.
Okay, let's pivot slightly. One of the big theoretical advantages of byte-level modeling is handling diverse languages and character-level nuances. Did the experiments bear this out?
Absolutely. This is where AUNet shows some really unique strengths. On multilingual MMLU, they saw clear benefits for other Latin script languages.
Like French, Spanish, German?
Exactly. Average gains were around 3 points for Germanic languages, 4 points for Romance languages compared to the BPE baseline. This really suggests AUNet is picking up on shared spelling patterns, shared morphology across these related languages. Things a fixed BPE vocabulary might miss if those specific cross-lingual patterns weren't common enough to become tokens.
Because it sees the underlying letters, the shared roots.
Precisely. It's learning a deeper representation. And this carried over into translation, too, on the Flores 200 benchmark.
That tests translation for many languages, including low-resource ones.
Right. They saw consistent gains when translating into English, especially from low-resource languages that might share characteristics with bigger languages in the training data. It shows AUNet is more robust to words. It hasn't explicitly seen out of vocabulary. Words are less of an issue. It can guess meanings based on subword structure.
That seems incredibly valuable for making models truly multilingual.
Huge potential there. And then there are the pure character-level tasks.
Like spelling a word backwards or deleting characters.
Yeah, things like spell, inverse spell, delete character. As you'd expect, AUNet, working at the byte level, performed significantly better on these tasks. The BPE model was better at standard word level tasks, which also makes sense. Its units are words or common subwords.
So there's a bit of a trade-off, depending on the task focus.
Kind of. Byte level gives you that raw flexibility. Token level gives you stronger priors about word units. But interestingly, the paper notes that even the BPE model showed some surprising ability on spelling tasks. It suggests that even with fixed tokens, if the model is big enough, it can sometimes infer character-level patterns implicitly.
Fascinating. So placing AUNet in the context of other other hierarchical models, how does it differ?
It builds on previous work for sure. There have been models like Megabytes, BLT, Hierarchical Spacebyte that explored byte-level inputs or hierarchical structures. But AUNet's combination is kind of unique. It brings together the multi-stage hierarchy, the adaptive pooling inspired by UNets, operating directly on bytes, and using these user-specified splitting functions. Many earlier models might have focused on just replacing BPE at one stage or used fixed pooling sizes. AUNet integrates all these ideas into a more flexible, end-to-end trainable system.
So it represents a more comprehensive take on adaptive, multi-scale, byte-level modeling.
I think that's a fair summary, yeah.
Okay, no research is perfect. What limitations or challenges did the authors identify?
The main one we already touched on is the reliance on space-based splitting right now.
Right, for non-space-based languages like Chinese, Japanese, Thai.
Exactly. They showed lower MMLU scores for Chinese with AUNet compared to BPE. So a really key area for future work is making the model learn where to make those splits, maybe using attention or some other mechanism, rather than relying on predefined rules like spaces. That would make it truly language agnostic.
That seems like a critical next step for broad applicability. Any other practical hurdles?
They did mention a technical challenge with large-scale training using FSDP fully sharded data parallelism.
That's the technique for spreading training across many GPUs.
Yeah. They found that with the deeper 3- or 4-stage AUNets, it became harder for FSDP to effectively overlap the communication between GPUs with the computation happening on them. Basically, the way the computation is structured in these deep AUNets didn't quite give FSDP enough work to hide the communication latency perfectly.
So a potential bottleneck for scaling to even more stages or larger models using current parallelism techniques.
Potentially, yeah, something engineers would need to optimize or work around.
All right. So wrapping this up, we've seen AUNet is this really compelling alternative to standard tokenization. It uses this UNet idea to process raw bytes, building hierarchical representations on the fly.
And the payoff seems significant. That infinite vocabulary, strong performance matching good baselines, and these unique advantages for multilingual settings and character-level stuff.
It definitely paints a picture of a future where language models could be, well, just inherently more adaptable, more aware of linguistic structure from the ground up.
Yeah, understanding language from its fundamental building blocks, the bytes, upwards.
So a final thought maybe for you, the listener, to ponder. How could models like this, these flexible byte-level models, change how we tackle really hard problems? Like cross-lingual transfer, truly breaking down language barriers.
Or maybe even enabling new kinds of communication, things that don't fit neatly into traditional words and sentences.
What new doors open when models don't just process language, but truly understand it, right down to its atomic components? It's definitely an exciting direction to watch.